Lenta, sóc una mica lenta, però no.
Bueno, benvinguts a l'ACA. Tenim el plaer de tenir el Colm Mulcahy. Thank you. És professor jubilat de la Universitat Catedràtica Emèrit de la Universitat d'Atlanta, de l'Spenn College en Atlanta. És irlandès, llavors ha estat uns dies a Dublín i per això ens ha visitat. Estarà una setmaneta aquí amb nosaltres. I bueno, és un dels grans divulgadors a nivell internacional, estudiós del Martin Gardner i de la màgia matemàtica. Ja us explicarà que té un llibre que és una meravella, té una columna que ha publicat articles pel Guardian, per moltes revistes de divulgació matemàtica i per moltes associacions a nivell internacional. I té una columna que ja fa molts anys que la porta, que és una meravella. Si busqueu Colm, així com cartes, Colm, que és el seu nom professional, doncs ho podeu consultar, d'acord? Ja dic, tenim el gran plaer de tenir-lo aquí, li vam convidar que ens fes una xerrada i I leave you with Colm. Okay, Colm?
Thank you.
We are yours.
Thank you. Thank you very much for coming. I hope to show you several interesting things in the next, 60, 70 minutes. I will start with a card trick. I will end with a card trick, and I will teach you how to do both of these card tricks. So let's start, and then I will show you some other things with shapes and fun things you can do with your students. This first trick I invented in, I think it was 2006. I was teaching a class, and I was teaching a topic which I did not enjoy teaching. I had a bad attitude about this topic. It's a very famous topic. I will tell you in 5 minutes what it is. But I thought, I don't like this. This is boring. And then in the middle of class, I thought, wait a minute. Card trick. So I got back to my office after the class, and I tried, and I had a new card trick. And now this is my favorite topic in mathematics, because it's very important. Okay, so we'll do this card trick.
Do we need to make some translation in some moment, or what do you think about it?
Well, if not,
No. Okay.
The important stuff is going to happen here. So I'm going to take these cards and shuffle them, and I'm going to take off maybe 5 or 6 cards, and I need help here from 2 people. 2 people, you're one person. You need to be able to do some mathematics. Now, first of all, momento. I need to make sure we understand the deck of cards. This deck that I'm using is, let's see a second here. Is it here? Yes. So full screen again is that, right? So the deck of cards, there are 52 cards. There are red cards and black cards. There are 26 of each. And these are called diamonds, diamantes. These are called spades. ¿Cómo se dice en español? Picas. ¿Y estos?
Trébol.
Y corzo. So, and you have 2, 3, 4, 5, 6, 7. There's aces. Ace for mathematicians is 1. There's 1 pip, 2 pips, 8 pips. So perhaps in poker ace is more valuable, but for us not so much. 1 pip. And then we get 10. And after 10, there is 11. The jack is 11. The queen is 12. And the king, is 13. So that's important, because we're going to do some addition here in a moment. Okay. So, these are the cards we're using. Now, I'm going to have 2 people to pick 1 card each. You can pick 1 card. And I need somebody maybe over here to pick the other card. You want to do it? Okay. So just sit there for a moment. Sit there. First, I'm going to mix the cards up. So I don't know what these cards are. I'm mixing them up. You tell me when to stop. My eyes are closed. Tell me when to stop.
Stop.
Okay. So you pick a card. And you pick a card. Now look at your cards. You can show them to each other. So you each see your cards, right? You remember your card, the number, and the suit, both. And you know his card, and you know his card, right?
I will know yours. Show me.
So you know your cards, right? So now put one back here, face down. There we go, face down. And put the other one maybe there, face down. Thank you. Now I'm going to open my eyes again. Now if you ever see a magician do this, the magic has already happened because they have tricks for getting those cards out. I'm not a magician, I'm a mathematician. So I have to use mathematics to find the card. So I'm going to ask you one question. What did the two numbers add up to? If you had a 3 and he had an 8, 11. If you had a 4, he had a 5, 9. What do the two numbers add up to? I'll close my eyes, you can communicate if you have to. Do you know?
Yes.
No?
Yeah.
Okay, what number?
11.
One thing? Okay, 11, right?
Yes.
Okay, so I'm going to mix these cards up more to make sure they're really mixed up. Now with 11 there are many possibilities. Perhaps 1 and 10. Perhaps 5 and 6. 9 and 2. 5.5 and 5.5.
11 and 0.
11 and 0. 12 and minus 1. So many possibilities. And then there are the irrational possibilities. Now, I couldn't help noticing you're not wearing glasses. No glasses. And you're not. Oh, you do have glasses, but I think we can work with those. I have special glasses. X-ray glasses. You're not wearing gloves. Your hands. You left your fingerprints on the cards. You left your fingerprints on the cards. Think about that. Yeah. Okay. So, fingerprints tell everything. Okay. So now you tell me what your cards were.
My was 8 of clubs.
And yours was?
3 of spades.
Would it be this ace of clubs, 8 of clubs, and that's yours?
Nasıl buldun?
Nasıl bir okey.
Nasıl buldun abi? Hoş geldin.
Now, did that look like mathematics?
Again.
Did that look like mathematics?
Not at all.
Did that look like mathematics? No.
No, it's not mine, it's mine.
There are tricks that you can do twice. It's possible to do some tricks twice. This one, it's possible to do it twice, but it's not such a good idea. If you hear a good joke in a nightclub, you don't say to the comedian, "That was so good, tell the joke again." It has the impact first time, and then you move on. So let me tell you what's going on here. So, well, we could try it again. So I'm going to mix these cards up. And then I'm going to take off 1, 2, 3, 4, 5, 6 cards. I'm going to mix them up. And you pick one. And you pick one. And now look at them. You each know each other's cards. And you have it, right? So now I'm going to open my eyes. So what do your numbers add up to?
Mine? No. 5.
What do the numbers add up to? Like before.
The end. Okay. 7.
7. So the last time I said, oh, it could be a 1 and a 6, or a 2 and a 5, or a 3 and a 4, or 2 3.5. It's 7, but I know instantly that it's a 2 and a 5, and I know which 2 and which 5 it is, but I don't tell you that. I hide the cards, I shuffle, I say, I'm looking for your fingerprints. That's magic. The mathematics is, I know it's a 5 and a 2, right? It's a 5 and a 2. And I knew which 2s, but if I told you now, you would think, how do you know that? So how do I know this? Okay, so there's two things going on here. There is some magic and there is some mathematics. It's a mathemagic trick. But it uses mathematics in an interesting way, I think. So let's see. Forget about the suits. Just focus on the numbers. The mathematics is numbers, numbers, numbers. So let's ask, what kind of cards could I have here? 1, 2, 3, 4, 5, 6, 7. There's a 7 in here. There must be a 7. There's a 7. Okay. So is it possible, the first time I did it, I think I did it with 5 cards. Is it possible that I was using these cards? Is that possible? I don't think that's a good idea, because if somebody says the total was 6, what could it be? It could be the 4 and the 2, or the 5 and the 1. That's ambiguous. We don't want that. So if I throw away the 5, does that help? No, because there's a total of 5 or 5. So in fact, if I use 1, 2, 3, I cannot use a 4, because then there is this ambiguity.
Okay.
So maybe I can use 1, 2, 3, 5. Now, can I use 1, 2, 3, 5, 6?
No, 7.
No. 7, 7. So I can't use that. So maybe I can use 1, 2, 3, 5, 7.
No, 8.
No, 3.
Yeah, we got 8 and 8, so we can't use that. So maybe 1, 2, 3, 5, 8 is a good idea.
Yes.
Now, if I use another card, can it be a 9?
No, because it's
Could it be a 10?
No.
No, 11. No.
Could it be a jack, which is worth 11?
Yes.
No.
Yes. Yes.
yes, 11.
2,
Yes.
sì, sì, perché sono
11 and 2 is 13, and 8 and 5 is...
13.
So that doesn't work. Could we use a 12?
Yes.
No.
Well, 1 and 12 is 13,
13.
5 and 8 is 13. Could I use a 13?
Yeah.
Okay.
Maybe.
No.
No. Ah, yeah.
There's a problem?
No, it's okay.
That's the problem.
No, because it's 14.
That's good. That works. Now, after 13, in a deck of cards, we stop at 13. Our universe is between 1 and 13. Have you ever seen these numbers before? Are these famous numbers in mathematics? 1, 2, 3, 5 Fibonacci numbers. Fibonacci numbers. So this trick works, the number part works if you use Fibonacci numbers. And that's a bit of a surprise. Now, as I said earlier, when I was teaching Fibonacci numbers, I always thought Fibonacci numbers were not so interesting. I mean, yes, they have many applications, but I had a problem with Fibonacci numbers. But now I think they're the best numbers ever. These are like the coolest numbers in the world because they make this trick work. So that's the secret of the numbers. Now, what's the secret of the suits? Well, I cheated. I had these cards at the top of the deck. So there's one trick where it's important that I don't shuffle too carefully. And I do that trick first. Because after this, there's no pressure. Everything else is 100% mathematics. This was a false shuffle. So watch again. Here's my shuffle. Here's my false shuffle. I was shuffling, but I'm careful to drop a lot there. But I do it quickly, so nobody's watching. And I can do it several times. It looks honest. It looks genuine.
I was thinking that you were a bad magician.
Yes, I'm a bad magician.
No, because of that, you said it's okay.
Yeah.
It's not shuffle.
It's a clumsy shuffle. Yeah. Now, if you are a professional, there are other ways to do this. But I'm a mathematician. So again, I'm shuffling most of the cards, but I'm making sure that the top 5 or 6 are the same ones. Now, I do mix them up. And I close my eyes, and people pick 2 and they add them up. But I know I have a 1, a 2, a 3, a 5, an 8, and a 13. But I also know which ones, the suits. I have memorized the suits. I have to remember the suits.
Yeah.
So that's not mathematics. But it's a magic trick. Some mathematics, some magic. And it uses mathematical numbers. So I'm now going to go through some slides here. And but maybe I started with a trick. But let's go back to the beginning. And let's see which of these arrows works. Yes. So these slides have two tricks. I've shown you one. I will explain more, and then I will stop and do some other things. And then at the end, we will come back and do one more trick, which I'll also explain. And you will be able to do these tricks later. So I'm only doing two tricks here, but I think card tricks that use mathematics are interesting because you can get students interested in mathematics in a new way. And well, as you will see from both of the tricks I'm going to do, there's more mathematics to consider. So new questions like, what if I change the numbers? So you can explore new things. It works for Fibonacci numbers, but it's not just Fibonacci numbers. It works for other numbers too. So predictions, mind reading. You know, I said I was looking for your fingerprints. Of course, I wasn't looking for your fingerprints, but he believed me briefly, I think. So, you know, I used algebra, not on that one maybe, but in some tricks you do. So my inspiration for this was a man called Martin Gardner, and he was a very famous American writer. And when I was a teenager in Dublin in the 70s, I used to buy his books. And I looked at the cover, and I saw a picture like that. Well, I saw a black and white picture, and I thought, oh, he's old, which he was. But then I was 17. And many, many, many years later, somebody said to me, oh, I'm going to meet Martin Gardner. And I said, Martin Gardner? He's alive? And he was. He lived a long time. He was 95, I think, when he died, something like that. So I got to meet him, which was incredible. I got to meet him about 20 years ago. And I took this picture of him. This is the picture I took. He was living in a home for old people, a retirement home. And he had a small room, and he had a bookcase. And I looked at the books. And every book was a book he had written. He wrote all of those books. He wrote all of those books. Most people never read that many books. He wrote over 100 books, which is incredible. So that's a joke in English. Standing by every word he ever wrote. That means he defends his words. But he's actually standing beside 100 books that he wrote. So he's most famous for Alice in Wonderland. He didn't write Alice in Wonderland, but he wrote the annotated Alice in Wonderland. And he did that in 1960. And it's the best-selling book he wrote. It's millions and millions of copies all over the world. So Alice in Wonderland was written by an English mathematician, Lewis Carroll. So he was a professor in Oxford, and he did mathematics, and he wrote these books for children. And he had jokes in there, mathematical jokes and all sorts of riddles. And Martin was very interested, and he kept writing them down. And somebody said, you should write a book about the book. So he did. And it's famous, and it's the first book of its type that annotated a book by somebody else. Now everybody does it. But he started that industry in 1960. In 1961, a man in Holland wrote to him, a man who did graphic drawings. His name was Escher. And Escher said, I really like your book about Alice in Wonderland. I like Alice in Wonderland also. And he said, oh, by the way, here's a painting I did. Yeah. And Martin Gardner looked at this, and it was mathematics. And that's how Escher became famous in the US. Escher was not famous before 1961. He died in 72. He got famous after he died. But in the 60s, Martin Gardner published about the mathematics in some of Escher's work. And that was done in the 30s and 40s. He did it later, but Escher was doing original mathematics, no training, as an incredible graphic artist in the late 30s and early 40s, during the war years, in fact. Salvador Dali used to visit New York, and he would go to a hotel and say, I am the great Salvador Dali, send me the smart people. So Martin Gardner met Salvador Dali. Dali had done a painting of the crucifixion, 1956, on the hypercube, and he was interested in mathematics. So they had several meetings. So Gardner met all these amazing people. He was friends with Asimov. So he wasn't a mathematician. He was a writer, he was a philosopher, but he wrote a lot about mathematics and popularized mathematics, and probably had more influence than anybody in modern times with mathematics popularization. And his legacy lives on here in some of the exhibits in the museum, so we're very happy to see that. So I'm involved with the institute that promotes his legacy, and we have conferences and so on. And if you're on Twitter, WWMGT, what would Martin Gardner tweet? He wouldn't tweet about politics, although he had opinions on politics, but he would tweet interesting things. And we have lectures every month on the 21st. Today is the 19th, so Friday, at 6 o'clock Barcelona time on Zoom. there will be a talk about optical illusions. He also wrote a book about optical illusions. He was interested in optical illusions, physics, philosophy, mathematics, art, and so on. So we also have a YouTube channel where you'll find lots about Martin Gardner. So as I said, he wrote a lot of, he wrote for a magazine called Scientific American. Between 56 and 86, he wrote about 300 columns. And there are many books that collect these. He wrote about things that are on the exhibition here in the museum, Soma cubes, Tangram's reptiles, the art of Escher, many, many things. And mathematical card magic. So when I first discovered card magic, I was, people who are good at magic start when they're very young. If I had started when I was very young, I might be good. But I didn't start till I was 40. And I got interested in the mathematics of magic, the connection. And the first trick I invented is the last trick in this book. So it is the oldest trick in the book, which in English is a joke, the oldest trick in the book. And that was 1999. So I only got into it in 1999. And then I was lucky to meet Martin Gardner and so on. Anyway, we've talked about the deck of cards, and we'll use that later. So now let's talk about the one we just did. This trick I call the little fibs, and I'll tell you why later. So 2 cards were picked, and I was told what the numbers added up to, and I think it was 11, the first time, 11. And I said, oh, it could be a 1 and a 10, it could be a 9 and a 2. But I knew instantly, but I didn't tell you, that it was an 8 and a 3. That's easy, I'll tell you why later. Secondly, I knew what the suits were because I cheated. I remembered the suits. I gave you a free choice from 6 cards. And then I showed you what could those numbers be. If you start with a 1 and a 2, it has to be 1, 2, 3, 5, 8, 13. But that's not quite true, because you don't have to start with 1 and 2. I'll show you some other possibilities a little later. So I claim here at the bottom, when numbers are added up, it's possible to take them apart. That's not true in general, of course. But think about multiplication. If I tell you I multiplied some numbers together and I got 15, you would say, well, it must have been 3 and 5, or 1 and 15. So decomposing into prime factors is pretty understood. We're decomposing using addition here. You say, well, it's not the same. Yes and no. So, the second secret I've already told you. Card flipped over. I shuffled, but I didn't do a proper shuffle. A proper shuffle would be like this, where it goes all the way. But I cheated and made sure that 5 or 6 cards were from the top. So that's a false shuffle. False shuffle. The mathematics is about numbers. So here's secret number 3. You memorize the suits, and these are the numbers that we used. A 1 and a 2. And of course, this famous sequence can be derived by taking a 1 and a 2 and adding them to get 3, and then adding the 2 and the 3 to get 5, and the 3 and the 5 to get 8. After 13, mathematics is interesting, magic not so interesting. So we have to stop at 13. Now you might say, well, why not start with 2 1s? You can do that. But if I had 2 aces in there, that would be a problem, because if the total was 6, I would know it was an ace and a 5, but I wouldn't know which ace if there were 2 aces. So for me, I do not want 2 1s at the beginning. I don't want a 0, I don't want 2 1s, I want 1, 2, 3. If I'm going to start with 1, I want to go on to 2. And these are the ones I used, and it's a particular order. Chased is a word that the consonants represent clubs, hearts, spades, diamonds. It's one possible order. If you play bridge or poker, you might have a different order that you think is a good order. You just have to remember. So I had an ace of clubs, 2 of hearts, 3 of spades, 5 of diamonds, then I have to repeat because of course there's only 4 suits. So those are the numbers I used. And these are the smallest Fibonacci numbers. So I call the trick, well, I have 2 names for it. Additional certainty is one name, and the other name is little fibs, because a fib is an abbreviation for the word Fibonacci, but also fib is, what's it, miento?
What?
Miento, a lie?
I am.
Lie.
Mentira.
Mentira?
It's a lie.
Yeah. So a little fib. No, little children tell little fibs. Yes, I finished my broccoli. Maybe not. Maybe it's on the floor. So, you know, it's a little fib. So, because I told some fibs. I said, "Oh, the cards are shuffled." Yeah. I have no idea what these cards are. Yeah. I don't know which one's which, but I do know which cards they are. So those were the little fibs I told. Now it works because of the unaddition property. If you take those magic numbers and you add two of them together, it turns out that the sum can only be gotten one way. Every possible, no, okay. So the reason this works is because of something called the Zeckendorf representation. Zeckendorf was a man from Holland, the Netherlands, and he discovered a long time ago, before the war, just before the war, that the Fibonacci numbers have a magical property. Every positive whole number can be written uniquely as a sum of Fibonacci numbers if you make a special rule. One rule is you never repeat a number. So 6 is 1 plus 5. It's not 3 plus 3. 1 plus 5. And the second rule is you never repeat a number and you never you never use two consecutive numbers. So 8 is just 8. Yes, 8 is 5 plus 3, but for us it's just 8. So it's kind of the additive version of unique factorization into primes. When you say every number can be factored into primes, which we all say, it's not true. Well, 7 is 7 times 1, but is 1 a prime? Probably not. So we mean every number is a prime number, or it can be written as a sum of two, as the product of some primes. And here, every number is a Fibonacci number, or can be written as the sum of two Fibonacci numbers. So if a number is a Fibonacci number, we do not break it up, because 8 is 5 plus 3, and those that's adjacent, so we shouldn't break up 8. 8 is as it is. So this was published in 1972. Now the story of Zeckendorf is interesting. He was a doctor, a Belgian doctor, and he joined the army in 1939, and he became a prisoner in a prisoner of war camp, and he spent 6 years in a prisoner of war camp in Germany. He was very lucky to live. And when he got out, he went back to medical work. Actually, he also qualified as a dentist. So he was a doctor and a dentist and an amateur mathematician. And he discovered this in 1939. He told nobody. And in 1972, after he'd retired, he published it. And even now, it's not so well known. It's a beautiful, beautiful fact. We have more about it here. So, if you take the number 6, what's the biggest Fibonacci number less than 6? 5. So take 5 away from 6, you get 1. That's a Fibonacci number. So 6 is 5 plus 1. Now you could write it as 3 plus 2 plus 1, but you're using adjacent consecutive Fibonacci numbers. No, bad idea. You could write it as 3 plus 3. No, bad idea. 10. 10 is 8 plus 2. So if you had told me the total was 10, I would have known instantly 10 is not a Fibonacci number, right? But I would have known it had to be the 8 and the 2, not the 7 and the 3, because I didn't have those numbers there. For the card trick, we just take off the biggest Fibonacci number. So if the total is 20, it's a king. Okay, sorry. If the total is 20, that's not possible with two cards, because 20 can be written as 13 plus 7, which is 5 plus 2. Now, some numbers require many, like 51 requires 4 Fibonacci numbers. That's okay. That won't happen with the card trick if you only use 2 cards. And 13 is just 13 as its representation. So why don't we teach this to children? We teach them about prime numbers. One reason is we don't know it. Most people don't know. Most mathematicians, 99% really of mathematicians do not know this fact. It's unbelievable. So I read this in a book that I was teaching from. A beautiful book. The book is called The Heart of Mathematics. That's all you need to find it. Came out about 95, 96. Beautiful book, The Heart of Mathematics. And it's mathematics more interesting. It's not for engineers or scientists. It's mathematics for people who don't like mathematics. And this fact was in there. And I was teaching this, and I didn't understand it because, I was teaching it the first time. And then in the middle of teaching, I said, wait a minute, card trick. I can get a card trick out of this. And it's a very popular card trick. The Zeckendorf representation. Now, other numbers work as well. Now, if you start with a 2 and a 1, and you do the addition principle, you add 2 plus 1 to get 3, you add 1 plus 3 to get 4, 3 plus 4 to get 7, and 11, 18, okay, after 18, forget it. But the 2, 1, 3, 4, 7, 11 is pretty good. Well, actually, there's a problem with the 2, because we have 1, 2, 3, and 4 in there. So 2 plus 3 is 5, and so is 1 plus 4. So forget the 2. Just start with the 1, 3, 4, 7, 11. It's only 5 cards, but they're different numbers. They're not Fibonacci numbers, but it still works for the card trick. So remember I said you shouldn't do the trick twice? The real reason is there is a high probability that at least one of the same cards will happen again. And somebody's going to say, I remember, we just had that card. But if I have the Fibonacci numbers here, and then I have 1, 3, 7, 4, 11 here, I have to remember suits. And I do a very clumsy shuffle because I have to keep 11 cards at the top. Maybe then I can do the trick twice, and people think I'm extra magic, but I think once is probably the best. But other numbers work. Now, that Lucas sequence is based on addition, but those next numbers are not. 1, 2, 4, 6, 10 works. They have that property that if you add any 2 of them, you will not get the same number as if you add any 2 more. You have a unique sums of 2. So it's like, what's going on here? That's a good question. That's something you can explore with your students. So does 1, 2, 5, 7, and a king. Those work. So there are different numbers that work. So you can do the trick different times and have completely different cards, and people will think you're a genius, maybe. So here's a question at the bottom. The problem with all of these numbers is that, I said that these are not the right numbers, but perhaps you have a set like this, and if you know the sum of 2, you know what the cards are. But if you think about the original numbers, we had a 1, 2, 4, 5, and an 8 and a king. Those are the Fibonacci numbers. If 2 people pick a card, and I know the sum, I know what the numbers were. And if I memorize the suits, I know everything. So what about if 3 people picked a card? Could I do it with 3 people picking a card?
Yeah.
Would it work with 3? Because that would make me seem even more magical.
No.
He knows. Why not? What?
16?
Yeah, 16 happens 2 different ways, which is kind of surprising. So a 1, a 2, and a king adds up to 16, and so do these 3. So if you can think quickly, that's okay, because if you get 16, just just don't be phased, and then later say, somebody had an ace, and if somebody has an ace, they'll go me, and if not, you'll say, no, just kidding. So there are ways to fish for information. It's not mathematics anymore. Okay? You can do that. But the other problem, of course, is with these numbers, if somebody says, okay, so suppose I said, I'm going to leave these cards here, turn away. I want you to take 2 or 3 cards. Don't tell me which. You decide 2 or 3, and just tell me what the sum is. Then I'd have a problem, because if you said the total was 8, maybe it was those 2, or maybe it was those 3. I wouldn't know which. So my last question here is it possible to have a set of cards, numbers, just the numbers, and all the subsets of all different sizes have different sums? So I might say take 2 or 3 cards, or 4, I don't care. And from the total I would know everything. How many numbers and which numbers? It doesn't work with Fibonacci numbers. So that's a new question. I'm not going to tell you the answer. It's a new puzzle for you to try. Okay, so that is that trick. And I'm going to stop that trick now and do something completely different. And for that trick, I needed to set up the deck. I'll do one more trick at the end. It doesn't matter. So I can relax now. I've done the hard work. The hard work was pretending to shuffle and remembering those suits. Now it's time to break out the wine. That's a good year. Okay, so let me tell you something about paper that's fun, and then I'll show you a video that's related to it. So here we have a strip of paper. Now, can I have a scissors, please? Can you just... Thank you. Thank you, thank you, thank you. Thank you. So, if I take this paper and I tape it, like this, and I take the scissors and I cut into the middle and cut all the way around, I will get, that's just a loop. If I cut in the middle, I will get 2 loops, right? 2 thinner loops. We all know that. But if I do a half twist before I tape it, now it's obvious here, and there's a name for this. It's a Mobius band. And Mobius gets the credit for inventing this, which I find kind of interesting, for 2 reasons. First of all, a year before Mobius invented this, Listing invented this in Göttingen. I was just there a month ago. They were very quick to tell me that the Mobius band is a listing band. But secondly, I don't think anybody invented this, because, I mean, look back at history. You have a late night, enjoying the vino, you have to take the sheep up to the upper field in the morning, you stumble out of bed, you put your pants on, you put your belt on. I mean, somebody has got to have put the belt on the wrong way. This must be thousands of years old. This is not a mathematical invention. But Listing and Mobius did it for a reason. They were exploring a new subject. 1858. Subjects, mathematics which was weird. And this is weird because the outside and the inside is the same. One-sided surface, very strange. However, if you do this with a long paper, maybe a meter and a half of paper with school children, I set this up before I go into the room. I have 3 of these, and I tape one the normal way, and I tape one with a half twist, and I tape one with 2 half twists. But if it's very long, nobody notices. So you bring in these 3 big loops of paper, and you get 3 children, and they're joined, and you start the cut, and then you say, I want you to cut near the end, but stop before the end, and then tell me what you think will happen. And let me show you what might happen. So let's see. We should do this here. So this is an example that I did a couple of years ago in Ireland. You see the 3 kids here in red. So they discovered that they had 3 different things because the initial conditions were different. I said I'm giving you the same thing, but of course I didn't give them the same thing. So what happens is, if the paper is no cheat, you will get 2 separate pieces. If there's a half twist, do you know what happens?
Yes, one.
You get 1 extra large one. And it has a half twist in it too, or is it a whole twist? It's something interesting about that. And if you do this, what happens? 2 interlocked. And if you do it again, then it gets
It's
interesting.
an 8.
Well, yes, it is an 8. Or infinity. So if you can do it, forever. What do you get each time? How many different things can you get? That's an interesting question. Other interesting questions are, if instead of cutting in the middle, imagine if you cut a third of the way in. Well, first time you get a thick and a thin calamari. This time, if you cut a third of the way in, you have to go around twice to come back. So what do you get? Is there something extra long? And how many twists does that have in it? And if you had done a whole twist and you cut a third of the way, can you get 3 interlocking like Borromean rings? Many, many possibilities to consider. But imagine that you had a donut or a bagel. Well, that's like this, except it's tastier. So if you cut a bagel in half to put in the toaster, you get 2 half bagels, right? Now, you can't take a bagel and put a twist in it, but you can cut along a twist. And if you cut a bagel along a twist, something very interesting happens. So let me show you that. Bagel twists. Yeah, so here are some pictures here. So at the top we have a regular ring, it's like a rectangular bagel. And then if you have a Mobius strip, if you move it, if you make it skinnier and wider, you get this top right picture, which superficially is a bagel, but if you look closely, it's not quite a bagel. So there's a bagel there. Now there's a way to cut a bagel. There's a video I'm going to show you where something very interesting happens. And here's the video. It's quite short. We have an ad. Now the audio, we're not getting the audio. So when the ad's over, we would like the audio. Thanks. So that's George Hart. George Hart is a very interesting mathematician, and this video is quite old. I mean, it's had 1 million views or something. It's probably 10 years old now. He is an American mathematician, and he's famous. He is the man who started the Museum of Mathematics in New York City. He designed most of the early exhibits there. He's not with the museum now, but he's the brains behind the mathematics in the museum in New York City, which, like this one, is very, very impressive. But this one guy came up with a lot of exhibits. So his name is H-A-R-T, not the same as Corazon Hart. And his daughter is also very famous, Vi Hart. In fact, when Vi Hart started, people would say, "Who's Vi Hart?" And the answer was, "Oh, she's George Hart's daughter." And now the question is, "Who's George Hart?" And the answer is, "Well, that's Vi's dad." You know Vi Hart?
No, but the V is 5.
V is 5 and 1 is, that's actually 1. So that would be 6 in Roman numerals, yes. So that's Victoria, but she calls herself Vi Hart. She makes videos. And some of those videos have had like 10 million hits. She is the best outreach woman in mathematics. Incredible videos. So just Google Vi Hart YouTube. Her videos are beautiful. She does mathematics and music, and she writes beautifully.
Dancer.
I'm sorry?
And dancer too.
She's a dancer too, yeah. She's a musician and a dancer. So again, it's like this is a 3D printed piece of plastic, and this is basically a version of this with the twist. So if you were to write along, the middle of this, you would have a line that comes back, but it twists around. And this, in fact, has a twist. Are you ready to watch? Are you watching?
Yeah.
Young man?
Look.
So, if you can do this with 2, Remember I said a half twist and a cut, you basically get a version of this. You might get a long one. If you cut a third of the way along, maybe you get 3 rings. You can 3D print a version of this that has 3 interlocking rings. It's more difficult, but it's possible. So let me ask you a question about some very common mathematical shapes. Maybe we'll put that in the chair. Please put that in the chair. Thank you. So here are some very common mathematical shapes. We have a circle and a triangle. And my question to you is there a 3D shape?
Yes.
With the special property that if you look, you see a circle, but maybe you look from a different angle and you see a triangle. The same thing. A cone, right? So you can combine those 2 shapes in a cone. Now, if I also put in a square or a rectangle, it doesn't really matter. That's a horrible square, but there we go. Pretend that's a square. Can you combine a square and a triangle? Is there a shape that's simultaneously a square from one perspective and a triangle from another perspective? Do you have an example? Good answer. What example are you thinking of? For a triangle and a square?
No.
So, these 2 are 2 aspects of a cone. These 2 are 2 aspects of a prism or a square-based pyramid, like the ones in Egypt. What about a circle and a rectangle at the same time? Cylinders. Okay. So any 2 of these we can combine. Can we do all 3? Is there a shape where you, from one angle you see a circle, from another angle you see a triangle, and from a third angle you see a rectangle or a square? Have you ever seen one? Most people say no, and then after a while they admit that maybe they have. But it's not so obvious at first. Can you tell me where you've seen them?
Like a cylinder could be shaped.
Is there an example in your home, perhaps? Do you see this in real life? It doesn't have a name. And if things don't have a name, we don't communicate about them. We probably don't think about them. And there is no Wikipedia page about them. You can't look it up because it doesn't have a name, which is weird. But have you seen one today? I saw one in my hotel this morning. The Novotel. Here. I saw one in the bathroom in my hotel.
You mean the cylinder and the hygienic paper that you can close and transform in a...
You don't have to do any transforming, it's already there. It's not the toilet paper roll. No, the toilet paper roll is a cylinder.
It's a cylinder that you can transform in a tetrahedron.
I've got one right here in my hand. But in the home, so I've been asking this question for many years, and usually when I show people, they say, "Oh, I've never seen one of those." But now, children tell me, "Oh, I have one in my bedroom. My mother has one in the bathroom. My father has one in the garage." There's actually 4 or 5 examples in a home, in a modern home, of this shape, which doesn't have a name. So maybe feel it, and don't say anything and give it to your neighbor. Just feel it. Don't show, just feel it. And pass it along. He's having an existential experience. Where's the camera?
But there's not...
No.
There's actually about 6 examples in a house, a modern house. I'll tell you in a minute. We'll wait till it gets halfway around. Also, you can make one tonight. If you don't have one at home, you can make one. And there's many examples in a modern house, but actually, we could have given Goya a knife and some simple instructions, and 1 minute later he would have an example. So it could have been done 200 years ago. Modern houses have many examples. So it's interesting because you have felt it, but you haven't quite seen it, but you kind of know maybe what it looks like. So, can you think of an example in the home?
Yes, she was saying that it's like a dryer.
Yeah. There are examples in the bathroom. For instance, a hair dryer might have an attachment, or a vacuum cleaner for getting the corners might have an attachment that looks that is this. You might trim, the barber might trim your neck with a razor that has this shape. A tube of toothpaste or shampoo. The shampoo in my hotel comes in, it's a longer version, but it's the same thing. So where is it now? Oh, you got, so, yeah. But isn't it odd? Because if we don't have a name for it, it's difficult to talk about it.
We need it now.
We don't call it, we squash it.
Yeah, I mean, you can make up a name, will it stick? I mean, until somebody comes up with a name, probably in industry there's a name. I mean, people who make this shape for shampoo tubes, maybe there's a name, but there's no mathematical name. But it has, you know, aspecto circular, rectangular, y triangular. And yet, if you don't, you know, it's hard to imagine it. But they are in the household now. Anyway, so why did I say Goya could make one? Just a cork from a wine bottle and a knife. You just take an ordinary cylindrical cork, and you just take 2 slices, so you can make a cheap one at home tonight. Very easy. This is another shape problem. These ones were easy. Let me get those ones a second. And, this one is easy for some people, but very hard for other people. I have given this to professional mathematicians who are geometers, and they've given it back to me after 30 minutes and said, I have no idea what I'm supposed to do. And then young people just get it instantly. It is the 3D version of, you know, a rectangle is 2 triangles. A rectangular box is 3 pyramids. The Chinese know this because they're taught it for thousands of years, but in Western culture it's not so well known. I mean, we're really very poor grasp of 3D. We live in a 3D world, and we can't invent new things if we can't. This is the basics, right? The volume of a pyramid is 1/3 the volume of the box that contains it, and yet it's hard for some people. This one is hard, and this is one I invented. So I'm going to pass this around. I'm not going to have slides about it. I'm going to pass it this way this time. It'll come back to you, don't worry. I'm hoping this young man here will be able to solve it. So the question is, what can you do with this? And actually, I'll tell you, I want a triangle. And it's a triangle, it's a triangle with a 90-degree angle, a right angle triangle. I'll give more information if you want. A right angle triangle, yeah. Did you get to play with that? You did? Okay, so I have a second video to show you here. And this is also very short. And this is an optical illusion. This is an object that looks like a circle. And it also looks like a square. And you see here a mirror. He has a circular object in front of a mirror, and the reflection looks like a diamond, which is a type of square. It's just a square rotating. And how is that possible? It seems crazy. Well, if you think about a mirror, I mean, imagine my computer screen as a mirror. If I put something here in front of it and I look down, I'm looking down at 45 degrees. The reflection is 45 degrees, so it's 90 degrees. So what you really have is a curve, made like out of wire, a curve that looks like a circle from here and looks like a diamond from there. And that sounds impossible, but it turns out it's very easy. Any 2 shapes you can do this with. Any 2 curves in the plane, you can come up with a 3D curve that looks like one curve from this and whatever other curve you want. And this video shows it to you in a very nice little way. This video was made by a Japanese engineer called Sugihara. It won a competition for the best illusion of the year, about 2016 maybe. This guy wins the competition half the time. He's won this competition, I think, 6 times. And the guy who won it 2 years ago is giving this talk on Friday, which you can all watch on Zoom, about ocular illusions. So he's this other guy who's giving the talk on Friday is another person who invents. This is very short, 1 minute. And here we go. I'm going to make them. Here we go. Here you have an arrangement of pyramids of diamonds, like an arrangement of pyramids. When he turns it around, we're seeing on this side of the mirror 6 circles and 8 diamonds? 8. So wait a minute, there's another problem. The diamonds and circles, but where do those other 2 diamonds come from? Well, they're the same as, they're the reflections of the gaps between the circles. So there's a lot going on here. Well, now it's getting stranger because now he has 4 distinct squares, and the reflection is 4 interlocked circles. I mean, the gaps. My head is really a problem. Yeah. So intersecting diamonds. Separate circles with a gap in the middle. You could drive a truck through that gap. Where's the gap in the real world? We're in the real world. That's the reflection. It's just extraordinarily brilliant. Yeah. And every year this guy does something. He has things rolling up hills and crazy. Sugihara, amazing. Now you can see on the right some links. I'll show you one of them very quickly because it's very quick. See this one here? This is an arrow pointing to the right. He's going to rotate it, and it will point to the left, right? You ready? Oh, I think. Okay, hopefully he will. This is a long video, but I think he will show us first. He explains also. Let's see. Okay, maybe we. Here we go. So left, right. That's it. I mean, then he explains mathematics. But he has designed a shape that looks the same even after you rotate it. And it looks unsymmetrical. It's just very, very clever, very creative. This guy does really cool stuff. Sugihara. Okay, so let's see. So how much time? How much time? It's 8 minutes past now. So. Okay. Well, let's see. So we're going to do a second card trick. I have some of the things here. Let's see. So, okay, we'll do this. And I need a piece of paper from that.
Okay.
Package, please. Yeah. So, thank you very much. So here's my question. I have this cylinder here, and it's very tall. And my question is, how tall is this compared to the circumference? Well, I know this, I know the answer, but when I look at this, my brain thinks that this is maybe 1.5, twice times the circumference. Some people think 3, 4, 1.2. So what do you think? How much taller is this than the circumference? Is it 1.5, twice, 3 times? What do you think? Sorry, 3 times? 3 times. 3 times. Is it 3?
Yeah, because there are 3 holes inside, isn't it?
So what do you think, when you look at this, what do you think? Does this look like it's taller than the circumference by a factor of 2, 1.5, something like that? 1, okay. 1. What do you think? How much taller is this than the circumference?
A circumference.
Yeah. Is it twice, 1.5 times as tall? It looks about 1.5 times to me. So,
Same.
well, if we take this piece of paper, it just happens to be pretty much exactly the height, right?
3.14.
So if this is 1.5 times, then if we rotate it, and we wrap it around, did it go around 1.5 times? No. Or twice? No. It didn't even go around once.
Yeah.
So apparently, the circumference is bigger than the height, which to most people, including my eyes, as opposed to my brain, is a surprise. This is a shorter distance than the distance around here. Now what is inside? You know the answer, right? Tennis balls. 3 tennis balls. So the height is 3 tennis balls. The width is 1 tennis ball. What is the circumference of a circle? It's 2 pi times the radius, which is pi times the diameter. So the circumference is pi tennis balls. The height is 3 tennis balls. Which is bigger, 3 or pi? You guys did better on this than any audience I've ever done this with. I can assure you, even engineers. This is actually shorter. Now I can just about stretch this with my fingers, and if I try to do this, of course I can't. But the piece of paper just happens to be perfect. That's 1 can high, that's 3 tennis balls. That's 3 tennis balls. Whereas the circumference is pi tennis balls. So the gap is the difference between pi and 3. That gap is 0.14159 and so on. Sometimes people remember a lot of digits of pi. People will remember 20 digits of pi, 100 digits of pi. There's no point. Ask an engineer. 10 digits of pi, 12 digits of pi, the most you ever need to know. It's a waste of time learning more digits of pi. But if you understand the digits of pi when you don't get this, well, you don't actually understand pi. So that's the gap in the decimal part of pi there. Actually, I have one here that is, this one here is exactly the same. This is taller than this, proportionally. This is pi times the width. And it looks like it's 4 or 5 times. That's the difference. When we see width circumference, our brain doesn't compute. It's just, you don't really compute. So if I was to cut this and unfold, it would be a square, which is very surprising. 3D printing. Cheapest, smallest, best 3D print ever. That is as tall as it is around, and it's very hard to wrap your head around that. You know, some people like me, as we get older, we get bigger. We look in the mirror and we say, no, not a problem. I'm not putting on kilograms, you know. We're just not very good at estimating circumference. So it's the same. It's the same. Let's see. So let me go back to the those guys there. Did you make something?
You are looking for a no triangle with 3 right angles. That is a no triangle.
What do you mean a no triangle?
because it's a hole.
Oh yeah, that kind of a triangle, yes. So what makes that triangle interesting is that, can I have that, can I borrow that back, please? Thank you. This is a difficult question, but this can be formed to make a triangle. And if you put it on this, it kind of almost self-forms. Minimal energy. It's a very special triangle because the three angles are 90 degrees, 60 degrees, and 45 degrees. 90, 60, 45. Did they teach you in school that the angles add up to 180? Bad teacher, bad teacher. That's only true for flat triangles. This is a spherical triangle. We're living on a sphere. The most famous triangle in the world, what? People say 3, 4, 5, right? Pythagoras triangle, 3, 4, 5, because 3 squared plus 4 squared 5. Yeah, that's a flat triangle. Here's the triangle that should be the most famous triangle in the world. London, the North Pole, and New Orleans. Easy to remember, and there's a right angle at the North Pole.
London and
London, the North Pole, and then New Orleans,
New Orleans.
in America.
Okay.
That angle is 90. London is 0 east-west.
Yeah.
New Orleans is 90 west. That is the most famous right angle triangle in my world.
Okay.
I don't know what planet you live on, but in my world, the most famous triangle, right angle triangle. And the geometry is always easier for right angle triangles, but the geometry of spherical triangles, it used to be taught in schools. When people were, navigating the world, sailing boats, Christopher Colombo, I mean, you have to know your angles and know spherical trig. Now it's forgotten. For the last 100 years, it's gone from the curriculum in most of the world. Maybe some engineers or, I guess, astronauts have to learn about it, but most of us don't. But it's a pity because we live on a sphere, and the geometry of that is interesting. The angles always add up to more than 180 on a sphere, because the corners are bulging in one sense. And so everything's different. The formula for Pythagoras' theorem, the long side is not the square root of a squared plus b squared, it's different. It uses trigonometry. The area of a triangle, different. Different. Spherical trig is different. And also, there's another type of geometry where the corners are pinched, and that's hyperbolic geometry. And on a saddle surface, if you take 3 points on a saddle surface and connect them by straight lines, you will get a triangle with pinched corners. The angles always add up to less than 180. If they add up to 180, it's flat, and that's all we teach. But we're living in a 3D world. Actually, the 3D world out there, space, is it flat? Cosmologists do not know, astronomers do not know. Is space curved? The Earth's curved. Is 3D space curved? How would you find out? Gauss tried to do this. Gauss went to 3 mountains in Germany and measured, and he got a bit of an excess of angle. I mean, it was a very crude measurement 200 years ago, but that was a proof that the Earth was spherical and not flat.
It's something like acertijo, what's in English? About this is a beer is walking just.
Oh yeah.
Yeah, this one.
Yeah.
And
you walk a mile north,
1 mile south, 1 mile, and which is the color of the beer?
Yeah, and this is another puzzle that Martin Gardner made famous in the 50s. And there are different answers. I mean, if you walk a mile south, a mile west, and a mile north, and you're back to where you started, it could be the North Pole, or it could be somewhere near the South Pole. In fact, there's an infinite number. There's an infinity of solutions near the South Pole also, which most people don't think of. So the answer is nice, but it's not unique. I mean, the polar bear, it could be either. It could be either.
It will be white anyway.
Well, whatever. That's biology, zoology. Okay, so let me see. One more card trick. I'm trying to think if there was something else I should show you here from these. I mean, with a large group of people, of course, it's always fun to do the birthday paradox. I was in a class a few months ago in Ireland, and there were maybe 40 kids in the room, and I wrote the word January on the board. I said, who has a birthday in January? And 3 hands went up. And the first kid was like the 4th of January, and the second kid was the 20th of January, and the third kid was the 20th of January. The third kid had the same birthday as the second kid. I thought it would take me 20 minutes to find a match, but I got a match immediately. It's incredible how easy it is to get a match with birthdays. There's 365 different possible birthdays, but they're not, I mean, they might be equally distributed, but it's very unlikely that you would get the same, that you would not get a match. You know, if you have 40 or 50 people, by the time it gets to 100 people, I mean, if there were 100 people in a big lecture room, I would bet €1 million. But I wouldn't tell you in advance, because you could find 100 people with different birthdays. But if you randomly pick 100 people, there's going to be multiple birthday matches. And even with 40, and with 23, it's a 50-50 chance, so don't bet money on that. But 60, 70 people, you know, it's a pretty safe bet. And it's really, really surprising. And kids are, you know, very surprised by that. There are other card tricks that take advantage of those ideas, but maybe we should finish with the ice cream trick, and then I'll tell you how it's done, and you can do the ice cream trick. So I want you to mix up these cards, make sure they're shuffled. So this time nothing, no tricks. Okay, so these are mixed up. Now, do you like ice cream? What is your favorite type of ice cream?
Dulce de leche.
Dulce de leche. Okay. So I'm going to take off enough cards to spell dulce de leche, and I'm going to mix them up. And I want you to tell me when to stop mixing. Tell me when to stop.
Stop.
Okay. You're going to get 3 scoops of pretend dulce de leche and 3 toppings of nata. Okay, you ready? D-U-L-C-E-D-E-L-E-C-H-E. This is the nata on top, the cream. Okay, that's the first scoop. We get 3. D-U-L-C-E-D-E-L-E-C-H-E. And the second scoop. Have you done magic before? Have you done magic before? He probably knows how to do this trick. Let's find out. D-U-L-C-E-D-E-L-E-C-H-E. Third scoop, third topping of cream. Now, I want you to press down with your hands, press down on these cards, concentrate, turn that top card into, the Jack of Spades. No, press down hard. No, just the top card. Focus, concentrate. Jack of Spades. Wouldn't it be incredible if this card was the Jack of Spades? Thank you. Let's have a look. So, first of all, if the Jack of Spades is here, something has gone terribly, terribly wrong. Don't see it. Ooh, Jack of Clubs, but not the Jack of Spades. So let's see if it's here. Something has gone even worse wrong. I think he succeeded. Very good. If this is the Jack of Spades, you have to give this young man who did all the magic a big round of applause. Is this the Jack of Spades?
Very
So, that trick was invented in Spain in the very early part of 2003. So it's 20 years old, and I've never performed it in Spain before, but I invented that in Las Rozas, which is in the suburbs of Madrid, where I was spending some time. And I was fooling around with another card trick, and I suddenly discovered something, and I thought, that's interesting. And I tried it with different numbers, and I thought, that's very interesting. And then the ice cream presentation was added later. But there's something mathematical going on here. So let's take a look. I have some slides here, and it should be these ones. So the 3 scoop miracle, or the ice cream trick. And I want to go to full screen, and that will be that. Okay. So many people say chocolate, doesn't matter, you can make it work. So somebody mentioned a favorite ice cream flavor. I had some cards, they were mixed up. So tell me again when to stop. We'll try chocolate this time. Tell me when to stop.
Stop.
Okay. So somebody says chocolate. So we spell out chocolate, C-H-O-C-O-L-A-T-E. That's not the same as dulce de leche. C-H-O-C-O-L-A-T-E. C-H-O-C-O-L-A-T-E. And I press down hard on the top card, and I turn it into the Jack of Spades again? Wouldn't that be amazing? Is it the Jack of Spades? So you do it 3 times. Mathematics, this is entirely mathematics. Well, it's 95% mathematics, which is pretty good. There's a little bit of magic in there. So you do it 3 times total. You're spelling out, that's reversing the order of some cards, and you drop on top. So let's take some cards in order, because that might make it more obvious what's going on here. So let's take out again, like we did for the other time. Where's there an ace? Ace. There's an ace. So I'm just going to, it doesn't matter about the suits, I'm just going to take out cards in order so we can study the mathematics. We'll do a 10 and a jack, which is 11. So here I have ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Let's take vanilla, right? Vanilla, which happens to be 7, but it doesn't matter. We can do 7, we can do 8. Mint chip, vanilla or mint chip? Which? Vanilla or mint chip?
Chip.
Mint chip? Okay, that happens to be 8. I don't want that one this time. M-I-N-T-C-H-I-P. So we have reversed the order of 8 cards, and we're dropping the rest on top. It happens to be 3. If I had spent vanilla, which would be 7, I would have dropped 4 on top. So now look, this is the 8 I reversed, and there's the original bottom 3 on the top. You do it a second time. M-I-N-T-C-H-I-P. Drop. Look. Now you see 3 cards together in reverse order. You see 4 in the middle, actually where they started, and then at the top you see, 5 in the middle, 3 at the bottom, 5 in the middle, and 3 on the top. So there's something going on here. And if we do it a third time, M-I-N-T-C-H-I-P, and I press down hard on the top card, what do you think that card is being? I know what that card is, obviously. But what do you think that card might be? Now I started with ace, 2, 3, down to 11. So which one is on top at the end?
Yeah.
The one that starts on the bottom. And even after the mixing, I just take a peek. I sneak a peek.
And the rest are in order? Or?
Well, yes and no. A lot of them are, yes. But the bottom card comes to the top. So this was published when Martin Gardner turned 90, which is 2004. And there's a video of it on Numberphile. Numberphile is a video channel that has many, like hundreds of thousands of views. Very good. Hundreds of videos, incredible stuff. But they have a version of this on there. So now, if you study it mathematically, you say, well, I start off with 1, 2, n. Suppose I'm dealing k cards from n. If I deal out the first k, what I'm doing here is reversing the order. That's, they start on the top. There they are here, and then I drop the rest on top. This looks bigger, but this is actually smaller than this because k is supposed to be. I have to deal out more than half. So vanilla is 7 letters. I need between 7 and 14 cards. If I have 20 cards, it will not work. Mint is too short, 4 letters. 4 to 8, that's a little claustrophobic. But chocolate is 9 letters in English or Spanish. So if I have between 9 and 18 cards, that works. He said dulce de leche, which is probably 12 letters. So I need between 12 and 24 cards. So it doesn't matter how many cards I have, but I make sure that the topping is smaller than the ice cream scoop.
Yeah.
So I deal out more than half and I drop the rest on top. It doesn't matter if it's 2 cards, 4 cards, as long as it's smaller. But it's very confusing. And then trying to see what happens the second time, it's like your head hurts. There's a better way to look. There's a better way to analyze this. In fact, there are 2 better ways to analyze this, plus the version in my hand. So instead of analyzing it the way I suggested there, think of the cards as having 3 parts: the top, the middle, and the bottom. So you're going to deal, at least, you have n cards, and you're dealing out k. So k is the length of the word. Vanilla, chocolate, dulce de leche, whatever. N is the number you have. N is less than 2k. Think of the cards as coming in 3 chunks: the top, the middle, and the bottom. And I've given you the size there. When you deal out the first time, you're dealing the top to the bottom and you're reversing the order. The little bar on the top means the order switched. The middle ones go to the middle, switched. The original bottom ends up on top, not switched.
The middle is always in the middle.
The middle's always in the middle, yeah. Now, what happens the second time? Well, that goes over here, switched. That goes there, switched, which switches it back, and that ends up. So it's possible now to understand what's happening.
Yes.
And if you do it 3 times, you will discover that the original bottom comes to the top. In fact, many cards that were on the bottom are on the top. In fact, more than half the cards that were on the bottom are on the top.
Yes.
And then the ones that were on the top are on the bottom. Now, I discovered this. I performed it by doing 3 spellings. I discovered it by doing 4, because if you do it one more time, what are we doing? Don't you delete? I can't remember. Vanilla. We're doing vanilla, right? Chocolate latte? Vanilla. Mint chip. Mint chip. Good. MINTCHIP. Now,
Original.
everything is back to where it started.
Yeah.
So when I first discovered it, I discovered that, you know, if you do this thing 4 times, it's like a false shuffle. It's like you never did it. But 4 times is boring for an audience. 3 times is half boring. So 3 times is better than 4. And then I discovered that the bottom card comes to the top. So all you need to do, mix the cards up. Just with the last minute, you say what's your favorite flavor. Just look at the bottom card. You're ready. You know the bottom card. It will come to the top. So the bottom card will come to the top, because you can check it with the cards. This argument works, but I will show you, as I promised, a third argument. So as I said, what's really happening is if you do it 4 times, it's as if you never did it at all. And that's a good idea, because suppose somebody gave you 7 cards, and you could say, I'm going to mix these up. Now just do this. 1, 2, 3, 4, drop. 1, 2, 3, 4, drop. If you do it 4 times, it looks like you're doing something pretty honest. But if you do it 4 times, actually you haven't changed anything. It's possible also to switch the numbers. I can run off 4, 5, 4, 5, and that also is the identity operation.
Okay.
There are many ways to generalize this. But here's the final, better explanation. Think of the cards as varying 13 colors. I had 11 when I demonstrated, but maybe I had 13. So white to black, 13 equal shades. Suppose I'm spelling mint chip, which is 8 letters. I'm taking the top 8, I'm counting them out in reverse order, and I'm dropping this on top. Now this is the bottom card, the darkest. That's the one I've looked at and remembered. The second time I do it, I'm counting off those 8 in reverse order, and I drop this 5 on top. And the third time I do it, I take those, and I put those 5 on top. But there we go. The bottom card went from there to there to there to the top. And that's why the trick works. And actually, 8 of the cards. And if you do it one more time, it's the same. So that picture, I think, explains it the best way. Question?
It's the same.
Yes. If you do it 4 times, it's the same. So that was invented in January, February 2003, and 20 years later, I finally get to perform in Catalonia, which is not too far from Madrid. Anyway, I'm finished. Thank you very much. Thank you.
For the subset problem
Yes.
with the cards, it's not possible, right? Is it possible with the cards? Okay.
Yeah, it's in. If you really want, I mean, you can figure it out for yourself, but it's. I can tell you where it is in here.
Okay.
But yeah, there is a set of 5 numbers.
Yes.
5.
Yeah, I mean, you can get a set. For us, we have a limit of 1 to 13. Within that, there are 5 numbers with the magic property that all the subsets of all the different sizes have unique sums. So there's only 5, not 6, only 5.
Okay.
If you want to make a 6 number, you have to have more than 13 cards. And you can extend that infinitely often. You can get 1,000 numbers that have 1,000 distinct sums of all possible sizes, but the numbers will be very, very big.
Okay.
And that's actually a question, a famous mathematician called Erdős, a Hungarian mathematician Erdős, who was very, very famous 20, 30, 40, 50, 60 years ago. He developed the mathematics that shows it's possible for any size. But for a deck of cards, you can find 5. Yeah.
Okay.
I mean, it's in here. I'll find the page, and he can take a picture of it and send it to you. when you give up. It's in the appendix. It's a parting gift. It's in there.
Any subset
Page
of
333 of the book.
any subset of
Any size.
any size.
Yeah, has distinct sums.
1, 2.
Well, the 5 numbers are different. So subsets of size 1, yes.
Okay.
A subset of size 0 has a sum of 0. The subsets of size 2 are 5 choose 2. That's whatever. But they're all different numbers, and they're different from the individual numbers. And the subset of size 3, they're all different. I'm just giving the richest possible collection of subsets. So at 5 you have 2 to the power of 5, which is what, 32. There's 32 different sums between 0 and adding them all up. They're all different from each other, which is surprising.
But powers of 2.
I'm sorry?
Powers of 2 will do. But you don't have.
Oh, no, okay, no. Powers of 2, yes, yeah. In fact,
the most efficient way. Right?
in the 1920s, there was a very clever card trick where you had an ace and a 2 and a 4 and an 8.
Yeah. That's the same.
But now, I mean, we're all sophisticated. We know about binary numbers. That seems like a silly trick to us. But in the 1920s, that was a sexy trick.
Okay.
We're more sophisticated. Yeah, powers of 2, powers of 3, they all work. Powers of 10 work.
Yeah. Powers of any.
Yeah. But there's not very many powers of 2 in a deck of cards. You don't even get to 16. So, you know. So this is more
There is a
disguised.
more efficient way of doing this.
The powers of 2 are very efficient, but they're not very impressive for this magic trick. This is more nuanced, more subtle.
We have to finish because the museum is closed at 8. So,
But I want to show you something in the exhibition, because you talk about Martin Garden, and there is something that Martin Garden didn't disclose.
Okay.
okay,
So
thank you very much.
Thank you.
Can I have my toys back
Okay, yeah.
for the next?